Hello, this is Jack Jackson. In this video, we're going to see how to apply integrals to compute work. So in physics, work is defined as the product of a force and a distance traveled. For example, if a constant force of 10 newtons is applied to an object and that object moves 3 meters, then 10 times 3 or 30 newton meters of work is done. Notice that this is a technical interpretation of the term work, which has Of course, the word work has other meanings in everyday language. Furthermore, notice that if no motion occurs, then no work is done. One can push as hard as they want as long as they want on a wall, but if the wall does not move, then no work is done. In the metric system, the standard unit of force is the newton, use a capital N for that, and 1 newton is 1 kilogram times a meter per second square. And the standard unit of distance is the meter, so the standard unit of work is the Newton meter, newtons times meters. In the American system, the standard unit of force is the pound, LB is the abbreviation, and the standard unit of distance is the foot, FT. So one of the standard units of work is the foot-pound, feet times pounds. Work for a constant force is easily computed using pre-calculus. In fact, all you really need is just multiplication from elementary school arithmetic, as we saw above. However, if we let the amount of force applied and or the distance parts of the object is moved be variable, then we need calculus to help us with the calculation. In the examples in this section, the motion will be in a straight line. In Calculus 3, we'll use vector calculus to generalize work calculations to even further applications. So let's just recall the basic strategy for setting up an integral to solve applications. So by now you should see that this basic strategy in integration applications is to divide the situation up into small pieces, approximate the thing we are calculating for each small piece using pre-calculus, often making assumptions that certain things are constant there, and sum up these approximations for each piece to obtain some type of Riemann sum. On those pieces, we usually think that on that piece, the shape is usually fairly simple and things are constant on that piece, at least in terms of our approximation. We then take a limit of this Riemann sum as the number of pieces approach infinity and their size approaches 0, thereby producing a definite integral that gives the exact value of the thing that we're looking for. If we only need a decimal approximation, which is often the case in practical applications, then we can use a numerical integral such as Simpson's rule or the similar method programmed into your calculator or computer. If we want or need an exact value, then we apply the fundamental theorem of calculus to get to the integral. So that basic setup works for pretty much any kind of integral application. So if you think about how that's set up, then that can lead you to how to set up the integral. So how's that going to work in a work setting? So no surprise, calculating work follows the same basic strategy. We divide the object up into small pieces. We then approximate the work done on that small piece by assuming the force applied and the distance moved are constant on that piece. And maybe I should add, and the piece has a nice shape. Okay. And if the piece is small enough, then this approximation is relatively good. We then sum up these little pieces of work to get a Riemann sum for the total work done. Take a limit of the Riemann sum to produce a definite integral for the exact value of work done. Pretty straightforward, the same basic setup as we always do. So let's put this process to work in a few examples. So here's our first example. 100 foot length of steel chain is weighing 15 pounds per foot is dangling from a pulley. So there's a pulley up 100 feet above the ground or more, and 100 feet of chain is hanging down from it. And we're going to wind it on this pulley. We're going to wind it up, maybe like on a winch. And how much work is done in pulling that chain up to the level of the pulley? Well, in this problem, The linear density of the chain is a constant 15 pounds per feet. So if we break it into small parts of the same size, say maybe just look at one link or even a fraction of a link, then the force applied matches the weight of that little piece. And this is a constant force. Okay. However, the amount each piece moved is variable. The link at the bottom of the chain is moved 100 feet. The one in the middle moves 50 feet, and the one at the top really doesn't move at all. So the distance is variable, so calculus can be used to calculate the work done. So let's consider a small piece of chain. Let y be the distance from the piece of chain to the pulley. The length of the piece of chain is then delta y feet. So kind of here's our picture. The pulley's up here, chain's right here, starting 100 feet above the ground, or above the bottom of this. The ground's down below that somewhere. It's just kind of hanging there. And here's a little piece of it. Where is it? Well, it's a distance y from the top. Its length there is delta y. Of course, once we take the limit, the delta y becomes dy in the integral. Now, the weight of that piece is 15 pounds per feet times delta y feet. Notice that delta y has a unit, in this case feet, and it has a physical meaning. It's a length. It's an actual length. And once we take the limit, delta y becomes dy, so we're going to think of dy as some infinitesimally small length, but it still retains the units no matter what. So it always has the same units as delta y. The dy is not just notational. You can't leave it out when you write down the integral, and it has a real meaning in the problem. In this application, we need to think of dy as an infinitesimally small change in length with feet as its units. Thus, the force applied on the piece is 15 delta y pounds, and we will consider that the distance moved for that piece is approximated by a constant distance of y feet. So this y is how many feet we're moving here. Y is 100 at the bottom, y is 0 at the top, and so forth. So how much work is done in moving that one link up, let's say? Well, its length the link is delta x, or delta y, and it's times 15, and it's moved by some distance y for that kth link. And then we want to sum that up from k equals 1 to n for all the links, and this gives us a good estimate of the amount of work done. And of course, delta y is just the total length of the chain divided by n if we want to divide it up into equal size pieces. So now we take the limit as n approaches infinity to get the following integral. And so once we take the limit as n goes to infinity, this becomes just 15y. This becomes dy. The sum becomes the integral. This s becomes that s. The sigma becomes the long skinny s for the integral. And that's the integral. Okay. So not too hard to find an antiderivative here, which y squared divided by 2. So we have 15 halves y squared. 15 halves I bring out front and evaluate from 0 to 100. So it's 100 squared minus 0 times the 15 halves is 75,000, and the units are foot-pounds. Notice the units on 15 are pounds per foot times y, which is feet, times another y, which is another feet. So we end up with, when everything cancels out, of one of the feet and the top and bottom cancels, we're left with a foot in the top and a pound in the top. Foot-pounds, that's an appropriate unit for work, so that's good. Dimensional analysis like that is always a good thing to do to help make sure you kind of got things going the right way. You might notice that the chain moves an average of 50 feet. Some of it's moving, from 0 to 100. It's moving on average 50 feet, so the center of the mass moves 50 feet. Because it's a uniform chain, the center of the mass will be exactly 50 feet from the top. The total weight of the chain is 100 feet times 15 pounds per feet, or 1,500 pounds. And notice that 1,500 pounds times 50 feet is 75,000 foot-pounds. And so notice that the work is equivalent to the work done by placing all the weight at the center of the mass and moving it by the fixed distance. Which, of course, so once you understand that, then you can probably do this without calculus. But that should not be a terribly surprising result. Here's one for you to try. A 28-meter uniform chain with a mass of 20 kilograms is dangling from the roof of a building. How much work is needed to pull the chain up to the top of the building? See if you can work it out. Come back when you're done. Press pause now. Well, here I set up the integral first with the units specified and then once without the units, cluttering up things. The force applied is the weight, which is the mass times acceleration due to gravity. Notice this time we were given a mass, not a weight of the chain, right? So there's a difference there. Force is mass times acceleration. A weight is a force. Up here we were told a weight. We're a weight per pound, pounds per foot, a weight density, and a length. Here we've got a mass this time. So 20 kilograms is there. So we need to convert that to a force, a weight. So we'll do that. So that's a Newton is a kilogram meter per second square. So if we'll just multiply this kilograms by how many meters per second square, well, what meters per second square? It's 9.8 meters per second square because the acceleration due to gravity, which is what's causing the force there. So that acceleration times the 20 kilograms works out to be the density. So the density, if you multiply that out, let's see, 20 kilograms per 28 meters is the density, the linear density, right? So multiplying that by this by dH, we'll talk about the height of it. So I used h this time instead of y. It doesn't really matter what variable I use there. So dH will produce a mass. Multiply the mass by acceleration of gravity to get a weight, which is a force, and the distance traveled for the piece is h. The picture is kind of similar to the last picture. So integrating force times distance gives us work. So work is the integral from A to B of force times distance. The force, again, is going to be the 20 kilograms per 28 meters times 9.8 meters per second square times dH meters will be the force, and then it's moved to distance of h meters. So I've put all the units here. It's 20 kilograms is the mass of the chain. 28 meters is the total length. 9.8 meters per second square is acceleration due to gravity. The height is in meters and dH is in meters. Well, let's look here. One of the meters here at the end, say, cancels that meters. We're left with a kilogram meter per second square there. That's a Newton and a meter there. So the answer is Newton meters. That's the right unit. So that's a good sign. So now just getting all the units out of our way, here's what we have. 20 28s times 9.8 times h. Well, that's just linear. 20 over 28 times 9.8 works out to be 19,874.4. I think that's an exact value. And then we integrate just h from 0 to 28. Well, the antiderivative is 1/2 h squared. Half of that, 19,000 something, is this 9,937.2. And then evaluate h squared from 0 to 28. That's 28 squared minus 0. So it's just 28 squared times that 9,937.2, which is 7,790,764.8 Newton meters. All right, let's try this one. Gasoline at a service station is stored in a cylindrical tank buried on its side, with the highest part of the tank 5 feet below the surface. The tank is 6 feet in diameter and 10 feet long. The density of gasoline is 45 pounds per cubic foot. I guess technically I should call that the weight density. And assume that the filler cap of each automobile averages 2 feet above ground. How much work is done in emptying all the gasoline from the tank, which is initially full, into automobiles? In other words, we're going to pump this from there to the tank. And then we're going to do one more thing at the end. 1 horsepower is 33,000 foot-pounds per minute. For electrical conversions, 1 kilowatt is 1.341 horsepower. And let's assume the charge for use of electricity generated by a power company is $0.072 per kilowatt hour. Assume that the electrical motor in this gas pump at the station is 30% efficient. How much does it cost to pump all the gasoline from the tank into the automobiles? So 1 full tank. So let's look at a picture here. Here's a side view of this. So here's the end of the tank. Now actually it's going, say coming out of the screen towards you, a distance of 10 feet at constant feet. But this is a cross section. We're going to slice it across here. When we slice it, we get a little rectangular prism actually. This is the end of the rectangle, and then it's coming straight at you 10 feet, and of course, finishes up on the other side. Now this will change from being 0 width at the top to going up the biggest width here, which is 6, which is the diameter, and then working its way back down to 0 again, depending on what depth we're at. All right, it's 5 feet below the ground, so we get to decide where we're going to put the coordinate system. I'd put the coordinate system right in the middle of the circle. And it's a circle of radius 3, diameter 6, so it goes up to 3 here. 5 more feet up to the ground, that puts us up at 8, and 2 more feet up to where we pump it into the car, so that puts this car up at level 10. So the distance from here down to the point is 10 minus y. So notice if it was at here, let's say it was at 2, 10 minus 2 is 8, that's how far it gets pumped. It was down here at negative 2, 10 minus negative 2 is 12, that's how far it gets pumped up. Okay, so we're looking at the cross section there. So what do we have? We have a thickness of delta y, which will eventually become dy when we do our limit. We have our width across here, which I'm going to call w. But w is twice the square root of 9 minus y squared. So when you've got a positive x over here on this side, so the coordinate of this, wherever this b is, look at its x-coordinate. That x-coordinate is the square root of 9 minus the y-coordinate. We will get everything in terms of y. But that's only going to give us the distance from the x-axis out, so we need to double that. So 2 times the square root of 9 minus y squared will give us the width across here. Now then we've got to remember it goes out toward us and makes a rectangle, so that's going to be 10 times that for the area, and then times the thickness dy gives us a volume. Okay. And it makes a little thin rectangular prism. Okay, and we're going to take that volume and figure out, we have a weight density for volume, so we multiply that by the pounds per cubic unit, cubic foot, I guess it is. Yeah, all the links are in feet. When we get that volume, it'll be in cubic feet. Multiplied by pounds per cubic feet, we get the pounds for that. Then we have to multiply it by this distance here, which is 10 minus y. That'll give us our work done for that little slice. Add up all that for all the slices, take a limit, and we have our integral. Don't forget there are units on the y, on the dy as well. So work is force times distance. Okay, so it's y. Y is running from negative 3 up to 3. Our distance moved is 10 minus y. Our force is going to be the density, I'll call it rho here, times A. It's actually a weight density. Okay, and then actually, tell you the truth, what we usually do is we usually use lowercase delta for a weight density and rho for a mass density. So anyway, whatever, it doesn't matter what letter we use for it. It's the density, which is 45 pounds per cubic feet. And then we got the area times dy, which will give us the volume. The area is length times width. Okay, well, one of those is fixed at 10, but the width here is variable. It's given by this formula 2 square root of 9 minus y squared. So the length is fixed at 10. The width is 2 times square root of 9 minus y squared. And then we have this here. So if you look at this, we'll multiply these two together, you get square feet. You get feet on dy, so that's cubic feet. Pounds per cubic feet multiply and you get pounds times this feet gives you foot pounds, so that the units work out. So drop the units now to here. I take the 2 times the 10 times 45 is 900, brought it out front. And here I just used a calculator to find this out. Okay, but I could have used, I could find the antiderivative here. Break this into two parts. The second part, let u be 9 minus y squared. You got a y, you got a negative 2y dy. You got the negative y and the dy, so you can do that one by substitution. The other part, though, is going to require a trig substitution. Anyway, when it's all said and done, without going into all the details, you get 40,500 pi for an exact value, or about 127,234.5 foot-pounds. I rounded off to 130,000 foot-pounds. That's rounding off to, well, really only two significant digits, because, in fact, when we look up here, it looks like the weight density was given the two significant digits there. If we assume these other figures are exact, still that's kind of a limiting factor for us there. Now, the cost conversion is really just a large dimensional analysis problem. We just got to keep track of the units. So it's in dollars, 0.072 per one, that many dollars per 1 kilowatt hour, kilowatt times hours. 1 kilowatt is 1.341 horsepower. Now the kilowatts cancels. 1 horsepower in the top is 33,000 foot-pounds per minute. So now the horsepower cancels. You got 1 hour per minute. This puts the minutes will cancel here. The hour will cancel with that hour. So let's see what's left here. And then we have this many foot-pounds from what we just did. So should everything cancel out except for dollars? Let's just check and see. Let's look at the time. Hours cancels here and here. The minutes cancel here and here. Foot-pounds there cancels the foot-pounds there. Horsepower cancels here and here. Kilowatts cancels here and here. The only thing left is dollars. So we've got our right conversion. Each one of these factors, well, the second, third, and fourth factor are equal to 1, and the first and last factor, first one's a conversion factor was given, the last one is what we actually had up here in the amount of work. Now that would be saying that it was 0.00345 whatever dollars, but that would be assuming that there's no wasted energy. Okay, turns out that we said that the thing was only 30% efficient, so we need to divide by 30% to get the actual cost. So dividing this by 0.3 gives us this, or it rounds off to about 1.2 cents to each time we have to pump out the tank. All right, another type of thing that comes up is springs. So a spring will have if you just leave a spring alone, it'll kind of get to a natural length. And then it takes some force to either compress it or stretch it. Okay? And it turns out that the force needed to hold a spring a distance x from its natural length, whether that's compressed or stretched, is proportional to the displacement. So the force is some constant times x. Force is kx for some constant x. Now that's Hooke's law. Okay? So the question is how much, if we've got a spring that's a natural length of 1 meter, and it takes 10 newtons to stretch to a total length of 2 meters, how much work is done in compressing the string from its natural length to a length of 60 centimeters? Okay, so let's see what we got here. So the first thing is, in this problem, the natural length is 1 meter. Stretching to a length of 2 meters means we actually displaced it by 1 meter from its natural length. So using this, we can obtain initial conditions. So f of 1 meter is 10, which allows us to solve for k. See, k times x is 10, but x is 1. So k is 10 Newton meters. Notice k does have units. So next we compress the spring from a rest to 0.6 meters. Now once we find k is constant. It's not going to change for this particular spring. Different spring will have a different constant. possibly, but this one will be the same. So here we're as a displacement of 0.4. So we institute a coordinate system with the origin at the natural length, and we're moving the spring from 0 to 0.4 on that scale. So the displacement from the natural length is increasing from 0 to 0.4 meters. The force applied to a little piece of the spring is then 10x, and we're going to compress that little piece a distance of dx. And with this, we see the integral computes the force done. Let's see, I think this is 10. Okay, so what happens is the force is 10x. It's moved a distance of dx, and we go from 0 to 0.4. Well, that's pretty easy. We square that. Add 1 to the power, divide by the new power. It's 5x squared, evaluate from 0 to 0.4. That's 0.4 squared minus 0 squared times 5 is 0.8. So it's 0.8 Newton meters. Probably better if I put these zeros in here to kind of hold my place there. All right, so that gives you an example, a few examples of work. I'm sure there'll be some more in your textbook, but look at those over in your textbook and then try to work some homework problems, working out some work problems.